So let's have a look at what stability really is. And that's what we'll do in this lecture. We'll look at two types of stability. First one is static stability, and that's the most common definition of stability. And that is whether something returns to its equilibrium. So when we have, for instance, you see it indicated here, when we have a ball in the center of a dent, you will see that if it is moved to the side, that there's automatically a reaction which returns it to its original state. And that means that for a positive stability, we want a reaction which has an opposite sign to the original deviation. So if we move it here to the right, then the reaction is back to the left, back to the center. Then something is stable, and that's what we call positive static stability. You see the alternatives next to it in the center. If it would be a flat surface, and you move it to the side, nothing happens. And that's what we refer to as neutral static stability. So the initial reaction is neutral, zero. And of course, if something is unstable, it's not stable, then it's what we call negative stability. And that means that the original deviation results in a force which makes it even worse. So deviation and reaction have the same sign. If they go to the right, for instance, let's call this positive. If they're both positive, the deviation is positive, reaction is positive. If it's to the other side, if the sign of the deviation is negative and the reaction is negative, this is also negative stability, negative static stability. So positive static stability, opposite sign, return to the original position. Negative, it gets worse. Well, what does this mean for flight? Well, for instance, it's an aircraft. If it pitches down due to a disturbance, a little bit of turbulence, for instance, then if it has positive static stability, it will try to return to its original angle of attack, original angle, pitching angle as well. And this is called positive stability. If it has neutral stability, it will continue to move in the same direction with the same angle of attack, same pitch angle, it will move down. And this is what we call neutral stability. And of course, what can also happen if that it is negative, has negative static stability, then it will get even worse and will move further down. So this is static stability. And there is another type of stability, and that we call the dynamic stability. Because even if it's statically stable, the aircraft can still be unstable. So here it's indicated how this works. So if we have a positive dynamic stability, it is damped out. So it initially returns to its equilibrium, and the excitations get less over time, meaning it will eventually return to its equilibrium in a stable mode. If it's neutral dynamically stable, then it will keep the same magnitude. The excitations will keep the same magnitude, and then it's neutrally dynamically stable. And in case of a negative stability, it will even get worse, as is indicated here to the most right, in the most right figure here. You see negative dynamic stability. So even though initially, as you can see here, initially it returns to its equilibrium, so it's statically stable, in the end, it is unstable, but it's dynamically unstable. So those two types of stability are very different, and we'll have a look at what this means for the aircraft. With dynamically unstable aircraft, it means that if it has positive stability, there might be a excitation, might be a movement, but in the end it will damp. There will positive damping, and it will be dynamically stable. Neutral, it will keep the same magnitude, and unstable, it will get even worse. To see an example of dynamic unstable behavior, you can download a little video game which is called Stable Flight, which you can download from the website. And there you can try to control it in different control modes. And you can see how progressively it will become much harder to keep the aircraft stable. And in the end, it will result in a dynamically unstable behavior. Part because of the pilot actions. It's also called pilot-induced oscillations. And in fact, this might be what was going on in the video clips which we showed in one of the earlier lectures, earlier clips, where you saw the V-22 and the F-22 suddenly maneuver very aggressively and dynamically unstable. You can experience the same using this little video game. And you need to select a mode when the game starts. You need to press 1, 2, or 3 to select different control modes. And in each mode, it will become more difficult to control the aircraft, which you have to keep between two black bands to avoid crashing. So it goes up and down, and you can control it. But what happens with those 3 different modes? Well, the trick is that we introduce more integrators into the control loop. What does this mean? Well, an integrator is basically what is in between the speed and the position. So the speed is the derivative of position, which means that the location, so place, is the integration of the speed. And similarly, the speed is the integration of the acceleration is the integration of speed. So if you control the position of the aircraft directly, it's very easy. You basically, the position of your joystick is the position of the aircraft. But normally we control the speed. So if you move a joystick up, you influence the speed, and it's indicated here. You influence the speed. And this means in this way you can also influence the position. This is the sort of normal control, arcade game-like control that we know it. More realistically is it, however, to control the acceleration. So with our control wheel, we then control the acceleration, which is integrated to the speed, which is integrated to the position. So then we have 2 integrators in the control loop, and this is called mode 2. And that feels more realistically, but it's slightly harder. But to make it really dynamically unstable, well, without training at least, you will have a very hard time controlling mode 3, where we're actually controlling the change of the acceleration, which is then integrated into the acceleration, integrated into velocity and displacement. And this is very hard to control. So try this yourself and see what the effect is. And there were, in fact, aircraft in the past which were designed in such a way that, in effect, there were too many integrators in the control loop, and it was very hard to control this aircraft. The lifting bodies, of which you can see a picture here, part of the research, some of those lifting bodies experienced this phenomenon. And this meant that test pilots were put in this aircraft and were meant to fly an aircraft which they were unable to control without the help of computers, because the human mind cannot process 3 integrators in a control loop without being extremely trained. But there is a limit. Somewhere 2 or 3 is the limit to the amount of integrators you can control. And if you can control mode 3 in this video game, it's partly because you can see the speed and not just the displacement. But 3 integrators is very hard. And those poor test pilots were put in these aircraft to control it. So this is longitudinal stability that you see in the game. It's the pitch angle. But you can see the effect of stability in many aspects of the aircraft design. We first have a quick look at lateral stability. One example of the effect of the requirement for stability is the dihedral, sort of the V angle that the wings make, which cause it to return to its equilibrium when there's a little bank angle, when there's a little roll angle. Because of this configuration, it will tend to return to its equilibrium. And of course, an opposite dihedral will make it unstable. Also, the wing sweep assures a stability both for roll and yaw, because the different way the wings are experiencing the flow when there's a side slip or roll angle, and this will make it return to its original position. So many choices in aircraft design are made for stability, or aim at instability. If you want a very agile military jet, they on purpose make it unstable and then have a computer to allow you to control it. But this makes the aircraft very agile. Well, these are examples of how lateral stability influences the configuration of the aircraft. In the next lecture, we will ourselves do some calculations and designing of an aircraft configuration to make it longitudinally stable. And we'll focus on the static stability because the dynamic stability is mathematically much harder. So for now, we'll look at the static longitudinal stability. And this you will see in the next video clip.